Tonight, let me share a story. Look up. A red ember glows in darkness. That tiny ember is Mars, closer than you might imagine, and surprisingly connected to our own world. What secrets link its past to life on Earth? Join me. Let's explore how Mars once felt alive. Imagine a world with blue skies, white clouds, and vast oceans reflecting the light of a young sun. This is not just a fantasy. It is a possibility that scientists are exploring right now. The story of Mars is a tale of two worlds. One is the cold, dusty planet we see today. The other is a ghost of a world, a warmer and wetter place that may have existed billions of years in the past. The mystery begins with a simple question. How can two planets, born from the same cloud of cosmic dust and gas, end up so different? Earth became a vibrant, living world, teeming with complexity. Mars became a silent, frozen desert. Unlocking this secret is one of the greatest quests in modern science. It is a detective story written in the rocks and soil of another planet. We are trying to read the clues left behind over billions of years. These clues tell a dramatic story of planetary evolution. They speak of a world that once had the potential for life, but then lost it. The answer is not just about Mars, it is about our own place in the cosmos. Today, Mars is a harsh place. Its atmosphere is thin, almost a vacuum. The air is mostly carbon dioxide, and it is far too thin to breathe or to hold much heat from the sun. The surface is brutally cold, with temperatures that can drop far below freezing. Any liquid water on the surface would either freeze solid or boil away into the thin air. It is a static, rusty world. The red color comes from iron oxide, the same compound as rust. Mars is a planet that has, in a sense, died. But the evidence suggests that it wasn't always this way. We see signs of a more dynamic and active past everywhere we look. The contrast with early Earth is striking. Around 4 billion years ago, when Mars may have been wet and warm, Earth was also a water world. Our own planet was just beginning its journey towards life. The conditions on both planets might have been quite similar. They were rocky worlds, they had volcanoes, and they both had water. So, what happened? Why did one path lead to oceans, forests, and cities, while the other led to a desolate red wasteland? This is the central puzzle. To solve it, we must journey back in time, using the tools of science to reconstruct a world that no longer exists. Our fascination with Mars is not just about exploring another planet, it is a search for understanding ourselves. By studying Mars, we learn about the processes that shape all rocky worlds, including our own. We can see what happens when a planet's climate changes dramatically. Mars acts as a planetary laboratory. It shows us a different outcome, a different path that Earth could have taken. It is a stark reminder of how fragile a planetary environment can be. The story of Mars is a cautionary tale, but it is also one filled with wonder and the promise of discovery. It forces us to ask one of the most profound questions we can ask. Are we alone? The quest to understand Mars is driven by this deep, fundamental curiosity. We want to know if life has ever existed beyond Earth. Mars is the most accessible place in our solar system, where the conditions for life might once have been met. It had liquid water. It had a source of energy from the sun. It had volcanic heat. It had the chemical building blocks that life needs, delivered by asteroids, delivered by comets. If life did begin on Mars, it would mean that life is not a rare fluke. It would suggest that the universe is likely filled with life. This is why we send our robotic explorers on journeys of millions of miles. The scientific story we will explore is one of gradual discovery. It begins with simple observations from telescopes on Earth. Then the first flyby missions gave us our first close-up look at the Martian surface. We will follow the orbiters that mapped the planet in incredible detail, revealing ancient river valleys, revealing deltas. We will land with the Rovers, our robotic geologists on the ground, as they touch and analyze the rocks. Each mission has added a new piece to the puzzle. Each discovery has deepened the mystery and brought us closer to the truth about Mars's ancient past. This journey is for everyone. You do not need to be a scientist to feel the wonder of it. The story uses simple ideas. It is about water. It is about air. It is about rock. It is about heat. It is about cold. These are things we understand from our own lives on Earth. By looking at Mars through this lens, we can begin to see the story it has to tell. We can follow the evidence, step by step, and see how scientists build a picture of another world. So let us begin that journey. Let us travel to the red planet and uncover the secrets of its watery past. The most powerful evidence for a different Mars comes from one simple substance: water. Today, the surface of Mars is drier than any desert on Earth, but the land itself tells a different story. When our orbiters began mapping the planet, they saw features that looked strangely familiar. They found vast networks of valleys that looked exactly like riverbeds carved by flowing water on Earth. Some of these networks branch out like the roots of a tree, a classic pattern created by rainfall runoff over a long period. These are not small channels. Some are hundreds of miles long, suggesting that large amounts of water flowed across the surface for a very long time. Our rovers have given us an even closer look. When the Opportunity rover landed, it found tiny, round pebbles. Scientists called them blueberries. These small spheres were rich in an iron mineral called hematite. On Earth, this type of hematite almost always forms in the presence of water. Later, the Curiosity rover found smooth, rounded pebbles cemented together into a rock called a conglomerate. Close up, smooth, rounded pebbles embedded in Martian rock. Ancient stream evidence, just like stones in a riverbed on Earth. These pebbles were shaped and tumbled by flowing water. They are direct physical proof that a stream once flowed here. The size and shape of the pebbles even allowed scientists to estimate the water's speed and depth. It was likely a fast-flowing, ankle-deep stream. Beyond rivers, there is evidence for even larger bodies of water. Scientists have identified what appear to be ancient deltas. A delta is a fan-shaped deposit of sediment that forms where a river flows into a lake, ocean. The Jezero crater, where the Perseverance rover landed, contains a spectacular and perfectly preserved delta. We can clearly see the layers of sediment that were deposited as a river slowed down and entered a standing body of water. This tells us that Jezero crater was once a deep lake, possibly for thousands or even millions of years. Places like this are prime targets in the search for ancient life. Perhaps the most breathtaking idea is that Mars once had a vast ocean. In the northern hemisphere of Mars, there is a huge, flat, low-lying region known as the Northern Plains. Some scientists have proposed that this entire basin was once filled with water, forming a massive ocean that covered nearly a third of the planet's surface. They have even identified what look like ancient shorelines, faint ridges that trace the boundary of this proposed ocean. The evidence is debated, but if true, it paints a picture of a truly Earth-like Mars. It would have been a world with a water cycle, rain, rivers, lakes, a great northern sea. For liquid water to exist on the surface, Mars needed more than just water. It needed a thicker atmosphere. An atmosphere acts like a blanket, trapping heat from the sun through the greenhouse effect. It also provides the pressure needed to stop water from boiling away into space. The thin Martian air today cannot do this. So, if Mars was once warmer and wetter, its atmosphere must have been much denser in the past. The big question is, where did that atmosphere go? The answer seems to lie in the planet's size and its magnetic field. Mars is much smaller than Earth, only about half the diameter. A smaller planet cools down faster. The Earth's hot, spinning metallic core generates a powerful magnetic field. This field surrounds our planet like an invisible shield, protecting our atmosphere from the solar wind. The solar wind is a constant stream of charged particles flowing from the sun. Without a magnetic field, the solar wind can strip away a planet's atmosphere over millions of years. Evidence from Martian rocks suggests that Mars once had a magnetic field, but it died very early in its history, perhaps within the first billion years. Once the magnetic shield was gone, the solar wind began to erode the Martian air. Our MAVEN orbiter, which is designed specifically to study this process, has seen it happening today. It has measured particles from the atmosphere being blown away into space by the solar wind. Over billions of years, this slow, steady erosion could have transformed a thick, protective atmosphere into the thin, wispy one we see now. Volcanoes on Mars would have continued to release gases, trying to replenish the air. But they were fighting a losing battle against the relentless solar wind. The planet was simply too small to hold onto its air. This loss of atmosphere triggered a catastrophic climate change. As the air thinned, the greenhouse effect weakened. The planet began to cool down. As the pressure dropped, liquid water became unstable on the surface. The rivers stopped flowing, the lakes froze over, and the Great Northern Ocean, if it existed, disappeared. The water froze into vast underground glaciers, or the water was lost to space along with the atmosphere. Mars transformed from a potentially habitable world into the cold, dry planet we know. It is a powerful lesson in how planetary geology and physics are linked to a world's ability to support life. If early Mars really was a warmer, wetter world, it raises the most exciting question of all. Could life have started there? On Earth, life began very early, when our planet was still young. The basic ingredients for life, as we know it, are simple. You need liquid water, which we have seen strong evidence for on Mars. You need a source of energy, the sun, geothermal heat. And you need the right chemical elements, especially carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. These elements form the organic molecules that are the building blocks of all life on Earth. Did Mars have these building blocks? We know it did. These elements are common throughout the universe and were present in the dust cloud that formed our solar system. Missions to Mars have confirmed their presence in the rocks and soil. More excitingly, the Curiosity rover discovered complex organic molecules preserved in ancient mudstone inside Gale Crater. These rocks are over 3 billion years old. The discovery of organic molecules is not proof of life. These molecules can be created by non-biological processes, but it is a critical discovery. It tells us that the raw materials for life were present on ancient Mars. The next step is to look for biosignatures. A biosignature is a sign of life, past or present. It could be a fossil, a tiny structure left behind by a microorganism. It could be a specific type of complex organic molecule that is unlikely to be made without biology, or it could be a pattern in the chemical makeup of a rock that points to the influence of living things. Finding a biosignature is incredibly difficult. On Earth, the oldest signs of life are subtle and still debated by scientists. On Mars, billions of years of harsh radiation and chemical processes have likely destroyed most of the evidence on the surface. This is why our search for life on Mars is so careful and methodical. We have to look in the right places. We need to find ancient environments that might have not only supported life, but also preserved its traces. The delta in Jezero crater is a perfect example. On Earth, river deltas are excellent at trapping and burying organic matter, protecting it for millions of years. By drilling into these ancient deltaic sediments, the Perseverance rover is collecting samples from one of the most promising places to look for a Martian biosignature. These samples are being sealed in tubes, waiting for a future mission to bring them back to Earth. We have learned almost everything we know about ancient Mars from our robotic explorers. These incredible machines are our eyes, hands, and laboratories on another world. They are an extension of human curiosity, traveling across millions of miles of empty space to carry out our scientific quest. There are two main types of missions. The orbiters circle the planet from above, acting as our spies in the sky. They create detailed maps, study the atmosphere, and use special instruments to identify different types of minerals on the ground. They give us the big picture and help us decide where to send our landers. The landers and rovers are our geologists on the ground. They are the ones that get up close to the rocks. Missions like Spirit, Opportunity, Curiosity and Perseverance have completely changed our view of Mars. These rovers are marvels of engineering. They are solar-powered or nuclear-powered chemistry labs on wheels. They carry a suite of advanced scientific instruments. They have cameras that act as our eyes, robotic arms that can drill into rocks and scoop up soil, and sophisticated spectrometers that can analyze the chemical composition of a sample on the spot. They are our hands, touching the surface of another world. Every rover mission has made game-changing discoveries. The Spirit and Opportunity rovers, which were only expected to last for 90 days, explored for years. Opportunity was the one that provided definitive proof of past liquid water on the surface, finding those hematite spheres and rocks that could only have formed in a salty sea. The Curiosity rover, a much larger and more capable machine, landed in Gale Crater. It confirmed that the crater once held a long-lasting freshwater lake with all the chemical ingredients necessary to support microbial life. It was a habitable environment. The most advanced rover yet is Perseverance. Its primary mission is astrobiology, the search for signs of ancient life. It landed in Jezero Crater specifically because the orbital data showed it was an ancient lake with a river delta. Perseverance is not just analyzing rocks, it is collecting them. It is drilling core samples about the size of a piece of chalk and sealing them in ultra-clean tubes. The plan is for a future mission, a collaboration between NASA and the European Space Agency, to travel to Mars, pick up these samples, and bring them back to Earth. This Mars sample return campaign is one of the most ambitious projects in the history of space exploration. While the evidence for a wetter past on Mars is strong, the story is not simple. The scientific community is engaged in a fascinating debate about what that past was really like. Not everyone agrees on the details. One school of thought, often called the warm and wet model, envisions an early Mars that was very much like a young Earth. Thick atmosphere, warmer temperatures, global water cycle, rain, rivers, large northern ocean, the most promising environment for life to begin and evolve. However, another group of scientists supports a different view, often called the cold and icy model. They argue the young sun was too faint to keep the entire surface above freezing. Mars was a mostly frozen planet. The valleys were carved by meltwater from glaciers and by ice sheets. The lakes, if they existed, were likely covered in thick ice. Water might have flowed only during short, temporary warming periods, perhaps triggered by massive volcanic eruptions that released huge amounts of greenhouse gases, or by large asteroid impacts that melted the ice. These two ideas are not necessarily mutually exclusive. The truth might lie somewhere in between. Mars could have been a planet of extremes. It may have had long, cold, icy periods punctuated by brief, warm, wet spells. The climate might have been cyclical. Perhaps the tilt of its axis changed over time, leading to periods of intense summer melting at the poles. Or maybe the volcanic activity was episodic, creating temporary habitable conditions before the planet froze over again. This would make the emergence of life more difficult, but not impossible. Life on Earth is resilient and can survive in extreme environments. This debate is a healthy and essential part of the scientific process. It pushes scientists to gather more data and to refine their models. The warm and wet camp points to the branching river valleys that look so much like they were carved by rain. The cold and icy camp points to the climate models that show how difficult it is to keep the planet warm. The rovers on the ground provide crucial ground truth. The minerals they find, and the context in which they find them, can help us distinguish between a persistent lake and a temporary meltwater pond. Each new piece of data helps to solve this grand puzzle. The story of Mars is far from over. We are just beginning to read its most exciting chapters. The next decade of Martian exploration promises to be the most revelatory yet. The key is the Mars Sample Return mission. When those rock samples collected by Perseverance are brought back to Earth, they will be analyzed by the most powerful and sophisticated laboratories in the world. We will be able to study them with instruments far too large and complex to send to another planet. Scientists will be able to search for biosignatures with a level of precision we have only dreamed of. We will be able to date the rocks with incredible accuracy, building a definitive timeline of when water flowed, when the climate changed. We can search for trapped bubbles of the ancient Martian atmosphere. We can examine the organic molecules with exquisite detail to see if they have the telltale signs of a biological origin. The answers to our biggest questions about Mars may be locked inside those small tubes of rock, currently sitting on the surface of Jezero crater. Bringing them home will be a monumental achievement for humanity, regardless of what they contain. The search for a second Earth on Mars has taught us so much about how planets work. It has shown us how a world can be born with all the right ingredients for life, only to lose them over time. It highlights the delicate balance of factors: size, a magnetic field, a stable atmosphere that allowed Earth to remain a living world. The story of Mars gives us a profound sense of perspective on our own planet. It underscores the preciousness of our own blue world, a rare and beautiful exception in our solar system. So, the next time you look up at that faint red dot in the night sky, remember what it represents. It is a world of mystery, a place of lost oceans, silent canyons. It is a scientific puzzle box waiting to be opened. And it is a mirror to our own planet, reflecting a different path taken through cosmic time. The quest to understand Mars is part of our quest to understand the universe and our place within it. The story is still being written, one mission at a time, and it invites all of us to look up and, wonder. Tap the next video to keep exploring.